Last year, Rockstar Games was hacked and they had the source code for GTA 5 stolen, and it only recently got publicly leaked online. So people started digging through the code, and someone discovered the remnants of what looked like a coding challenge that Rockstar would give to candidates who were applying to work at Rockstar. So I thought it would be a fun little exercise to just record myself attempting to do the coding challenge. I won't host the actual stolen source code, but I did create a question that is very similar. It's inspired by the original Rockstar code, and I thought, I'd give it a shot, pretend like I was doing it in an interview situation or something, and then, after that, maybe do some actual research and see if I can optimize the solution as much as possible. So here's the question. You might want to pause it and maybe attempt it yourself, see what you come up with, and yeah, it's a pretty fun little thing. So instructions are: find as many things wrong with the code as you can and fix them. Sort by set bit count is supposed to sort an array by the number of ones, or the set bits in the binary representation of each number. Make it work correctly as fast as possible. You'll be given points for style, speed, and correctness. So there's no mention here of memory optimization or space efficiency. So that's one of the things that I immediately, before anything else, I would probably ask the interviewer, like, is space efficiency an issue here? Can we trade space efficiency for time efficiency? So that's one of the things that I would clarify immediately. So another thing that I would clarify is we're sorting an array. So I want to know, should we sort in ascending order or descending order? I can just pick one because there's no interviewer. So I'm just going to say descending. It's not going to matter too much, but you should probably be clarifying these things. So start off with the count set bit function. It returns an unsigned integer, and which makes sense because we're using binary representations of numbers. So I'm guessing we're doing bit shifting. Count set bits takes an unsigned integer, initializes a result. While x does not equal 0, we do these operations. So if x equals 1, we increment the result, and then we do something to x. So I'm not 100% sure what this operation is. So if this was an interview, I would have to clarify with the interviewer. I would actually need help from the interviewer because I don't remember what this does off by heart. So for the purpose of this video, I'll just look it up. But yeah, I would need help in that respect. This operation, I understand what this is doing. I know it's an inclusive OR operation. I know what it's doing. But what's interesting is this is always going to be true because an inclusive OR operation on 1 will always be true. So either one of two things will happen. Either we'll have to use some other operation, or I'll have to just get rid of this code. But we'll come back to that, I suppose. We'll just keep moving on. So the function sort by set bit count. So we're sorting an integer array by how many set bits are in it, and we use this, and it looks like it uses this count set bits function. That's fine. So immediately you can see it's this time complexity of big O of n squared, because there's two loops and they both iterate over the size, which I'm assuming this is the size of the array, which I would clarify and just clarify everything you're unsure about. Clarify little things like that. So we call count set bits on this expression, which is immediately I can see that's wrong, because this expression will resolve to a Boolean, which will be sent to this function count set bits, which takes an integer. So there's going to be some implicit type conversions happening, and you can immediately see this is not what's expected to happen. So what it should look like, I'm guessing, is this count set bits So the count set bits of array I is less than or equal to count set bits of array j. That's what it's supposed to look like. And then if that is true, we do a swap. So I said before there would be sorting by descending order. I just chose descending order, so less than or equal should work for descending order. The swap looks fine, but there's some other things that I can immediately see that are wrong. This is what looks to be an insertion sort, and the issue you have with the insertion sort is the inner for loop is going to mess up the algorithm because j starts iterating at the index of 0, and this is not correct. So what it should do is start at I plus 1, and I'll show you why. So let's say we have an array of integers 8, 2, 7, 5. We have our I pointer and we have our j pointer. Currently what it's doing is we start on the first element, then we iterate j, move up. If they satisfy the condition, we do a swap. Which is fine, and then we can, iterate through the rest, and then once j has finished iterating, then we move up. I iterates. Now here's the problem that I can see is immediately j is set to 0 again. However, once we move I up in an insertion sort, this element has to be set in place. Like that's just insertion sort. It should never be changed once the outer loop has iterated past it, because it is set in place. It's in it. It's where it's supposed to be. So by setting j at a element that is already set in place, it's gonna break the entire algorithm, because there's a potential for another swap to be done if it satisfies the condition, and it's exactly the wrong thing that you want. So that's why instead of starting j at 0, where we have the set in concrete element, j should start not even where I is, because you don't need to compare an element to itself, but j should start at I plus 1. That way we know we're never gonna be swapping out this element that's already set. It's a very convoluted way of explaining that, but that's how I see it. So so what I did here was replaced j equals 0 with j equals I plus 1, because we never want to set we really never want j to be on 0. Oh, and yeah, another thing that I noticed is this should not be less than or equals. This should not be less than or equals. This should just be less than. If it's less than or equals, we're going to end up running out off the end of the array and outside of the memory of the array. That looks pretty good. Oh, okay. So it's an insertion sort, right? So it's big O of n squared time complexity, whereas n is the size of the array. We could use something like a merge sort, which is big O of n log n, which is better than O of n squared, obviously. But to actually implement a merge sort in an interview where you only might have 30 minutes is probably too, it's probably too much. If I had practiced implementing merge sorts over and over again specifically, then yeah, maybe I'll be like, hell yeah, I'll just smash out a merge sort. But I haven't practiced doing merge sorts. But I know it's much more involved algorithm than just an insertion sort. So ideally, I'd be able to do it, but not in an interview setting. Moving on to the count set. Yeah, so let's circle back here. So what's happening? So if the number is not 0, we check whether the OR operation on 1 is true, and it always will be. So we're always going to be counting a bit whether or not it's 1 or 0. So that's wrong. That's not what we want. So something has to change here. Then I ended up Googling this. So what this does is, so let's say we have the binary representation of the number 10. Looks like this, 1010. If we perform the right shift operation on 10 with the right hand operand being 1, essentially we remove the least significant bit. That's essentially what that operation is doing. So we remove the least significant bit, and then we shift the entire number to the right, which would cause the number to become 5. Given that in mind, let's look at what our algorithm does. So we check if the number or 1, which will always be true. Then we increment the result. Then we shift to the right by 1, meaning we remove the least significant bit and we shift the entire number to the right. Then we do it again. What this means is every single time we shift, we're going to increment the count or the result, which is not correct. It's not what we want. So let me run the algorithm through we'll test it with 10. So 10 looks like this, and then we do the OR operation on that, which looks on 1, which looks like this, and the answer will be 1 0 1 1, which is 11, which will resolve to true. And then what we do is we shift our number 10. So since this is true, our count or our result becomes 1. Then we shift the number, do it again. So 1 0 1 is our shifted number, and we do the OR operation on that, which is 0 0 1, which will resolve to 1 0 1, which is 5, which resolves to true. Since that's true, we increment our result to 2. Do it again for the shifted value. So the shifted value of 5 is now 2. So we do the OR operation on 2 and 1. Gives us 1 1, which is 3, which equates to true. Therefore we increment our result. We do it again on the shifted value, which is just 1 and 1 is true. Therefore our result will end up as 4. But you can immediately see that's wrong because there are only 2 set bits in 10. So we need another we need another operation because OR is not the right operation. Let's try it with let's just try it with XOR or something. Try it with AND. So let's do exclusive OR on 1. That boils down to 1, 0, 1, 1. Which will equate to true. So increment our result. Then we have to shift. Do the shift. Do XOR on 1, 0, 1, 0, 0, 1. That equates to that 1, 0, 0, which is true. So increment result. Again, shift that. Do XOR on where were we? 1, 0, then 0, 1 equates to 11. Immediately, that you can see that's true. That's wrong. So that's the not the correct operation because we're already at 3 for our result, and that's obviously wrong. Let's try AND, I guess. The AND operation. So 0, 0, 0, 1. That ends up being 0, which is false. So our result stays at 0. Then we shift. 1, 0, 1. That ends up being true because, well, let's just do it. So 0, 0, 1. That ends up being true. So we increment our result. Let's do it again on the next shifted number, which is 1, 0, 0, 1. That's 0, 0, which is false. And then finally, our final shifted number is 1 and 1, which will equate to true. And that's pretty good because that's looking promising because that's the exact number of 1s that are in our original number. So looks like here, instead of doing the inclusive OR operation, they wanted it to do the AND operation. I would really have to clarify that with the interviewer because I may have made a mistake in there. Yeah, before going too deep on that, like any further with that, I would definitely just be like, all right, am I on the right track here? Am I wasting my time here? Yeah. So there was one other thing that I thought about, and that is this count set bits is dependent on the size of, I guess, the size of the number. So the bit size of the number. So if you have a 32-bit integer, you're going to be calling. So each count set bits operation will be done 32 times, and we do that twice for each iteration of the inner loop. So that's n squared times. So there must be a way to do this in n amount of times. Like we could use an auxiliary array that stores the result of each count set bits. We could do something like this. Now we have an array full of the results of the count set bit operation, or the count set bit function. So that means we can just get rid of the count set bit function and we can do the comparison on the auxiliary array instead of the original array. But that would just mean that we have to sort the auxiliary array as well. So to do that, we can just do the same swap operation on the auxiliary array as well. That should eliminate the need to call count set bits n squared times, and now it's only being called n times. So now I'm just going to give it some input data, and we're going to have a look and see if it actually sorts properly in descending order. And that looks perfect. So this is descending order. This number has the most number of set bits in it, followed by 87, 45, 44, 88, then finally 1024. This has only one set bit in it, so that's looking pretty good. So yeah, that was my very basic attempt at it. I would have had to get help for sure because I had to Google a couple of things. Well, I had to Google what this operation is, and I never would have got that like if I was in a situation, an interview situation without help. So could do better next time. Always room for improvement. But this is a fun little problem. So I actually did some digging after my attempt, and it turns out that this function here, count set bits, it actually has a standard library implementation called pop count, which means population count. It counts the number of 1 bits in the value of x. So this would be better to use than what I currently have, because there are some, there are potentially many CPUs that use an actual optimized CPU instruction designed specifically for this cause. So if I were to replace this with this call right here with the standard pop count, in theory it would be even more optimized, because it's literally just doing like one CPU instruction as opposed to all of this. So yeah, if anyone has some suggestions on what else could be done to optimize this, like obviously implementing a merge sort would be better, but there's got to be other things that can be done with this. Yeah, let me know in the comments. Just yeah, have fun with it, guys. Thanks for watching. Bye.